All right, continuing with the optimization questions. I think we got 3 more, and then we'll be done. The third one's long, though. Okay, find the maximum area of a rectangle inscribed in an isosceles right triangle whose hypotenuse is 20 centimeters long. You're like, Mr. Bill, I don't even have the foggiest idea where to start. Let's draw a picture. Isosceles, that means 2 of the sides are the same length. I'm going to draw it so the hypotenuse is down. So see, isosceles, so those two are going to be congruent, and it says it's a right triangle. And it also tells me that this total distance on the bottom, the hypotenuse, it tells me that's 20. So it says find the maximum area of an inscribed rectangle. So I've got some rectangle inside. I don't really know what it's going to be. Maybe it's really narrow and tall, or maybe it's really narrow and wide, or maybe it's kind of towards the middle. I'm just going to draw some random point. And then, of course, that rectangle would go across and then down. So I've got this like area of the rectangle within that isosceles trapezoid, or triangle, trapezoid. All right, so that's 90. So I know these two angles would both be 45. So that's really nice. I'm going to call, let's call this distance right here, the width of the rectangle, let's call that x. So I need to know what this little measurement is, and then congruently on the other side it's going to be the same. So I'm going to put just a question mark for here. So I know right now, like x plus 2 of the question marks, that would give you 20. If you don't want to use the question mark, you could use y, or you could use z. I'm not going to use y here because I'm going to use y as the height of the rectangle. Okay, so I'm just going to use x, y, and then question mark. Okay, so I know the area of this triangle, or sorry, the area of the rectangle, it's x times y. And somehow I want to optimize this. I want to make that area as big as possible. But I don't want to have x's and y's, so somehow I need to get it down to either all x's or all y's. And this one has a lot of geometry at play. So let me kind of walk you through it. We have this picture. That kind of should help a lot. We have this dimension, which is x. We have this vertical, that's y. So the area is x times y. That's great. But I need to know what the y is in terms of x. And in order to do that, you need the question mark. Okay. So I know that's question mark, and that's x. So I know x plus 2 question mark is 20. So solve it for the question mark. Subtract the x, divide by 2. 20 minus x over 2. That is what your question mark would be equal to. Now let's also think. I'm going to just kind of take this little triangle, and I'm just going to blow that triangle up a little bit. So now I know the question mark. The question mark was 20 minus x over 2. I don't really know what the hypotenuse is, but then the vertical height right here, right, this was y. So the left side of that little triangle is y. The bottom was your question mark, which we now know is 20 minus x over 2. And then I don't care what the hypotenuse is, doesn't matter. But since this angle, we know the whole thing, right? It was isosceles right triangle, so I know that angle was 90. So I know these two base angles were 45. So I know that one's 45. I also know that rectangle is going to drop at a right angle, so I know that one's 90 degrees. So logically, I know this one's also 45. And what I know now is, hey, like not only is this whole triangle isosceles, then specifically this little triangle, even though my diagram may not be to scale, NTS, not to scale, that's okay. I know though, since this angle is 45 and this angle is 45, I know that this little triangle here, and also on the other side, those are also isosceles. And what I know about isosceles triangles is that the base angles are congruent and these base lengths are congruent. So here y is going to end up being that same measurement as well. So that question mark was important because the question mark ends up being the same value as the y. Since this whole thing is isosceles, I know those two sides match. You don't need to know what the whole side is, it doesn't matter. But specifically, I also know those two base angles are 45. Then you're looking at this little triangle. You know that angle was 45. You know the height for the rectangle, that creates it to be a 90 degrees. So that one's 45. So then this little triangle is also isosceles, so these two must be the same. And since this one is your 20 minus x over 2, that means y is also 20 minus x over 2, right? Lots of geometry. That was kind of the point of that whole class, is that you could think through some of these more complicated questions. But now I know an equation, right? I've got y is equal to 20 minus x over 2. Now I've got this kind of scratchwork equation that ties the x's and y's together. So now I can use this to make a substitution. The area is x times, but now instead of y, I'm going to substitute in what y is equivalent to. Okay, I'm just going to simplify it a little bit. You can have a 1/2 20x. I'm going to just take the 1/2 out to the front. Then you have 20x minus x squared. And so now I've got the area equation, and now it's based only, I guess I could have put it up here, the area equation only on the variable x. And now that I've got that area equation, and I got it down so that it's only one variable, now I'm ready to do the calculus. Now I'm ready to take the derivative, and since I have x's, I'm going to take the derivative with respect to x. But the calculus is to take the derivative and set it equal to 0. The 1/2 is just a coefficient, just copy it. Then the derivative of 20x would be 20, and then the derivative of x squared is 2x. You could simplify this if you want. Your derivative is just going to be 10 minus x. And then, of course, we would take that derivative, set it equal to 0, so I know x has to be 10. Okay, wonderful. So I've got one of the dimensions, and now I need to get the other one. If x is 10, 20 minus 10 divided by 2, 20 minus 10 over 2. So that means the y has to be 5. So I've got this combination with the x being 10 centimeters and the y being 5 centimeters. I've got a combination, and I know that's a critical point combination. I know both of these make that derivative equal to 0, but I need to check and make sure that these aren't going to minimize the area. I need to check and make sure that they're going to maximize. Again, you could do first derivative test. That's more work, though, to do the whole sign chart. You could do your candidate's test. That's more work to really do that whole table. Sometimes you want to do it, like on the next one we're going to. But here I think it's just easier to do the second derivative test. All right, so again, let's check. Here is your first derivative. So the second derivative is just going to be -1. That second derivative is less than 0. Therefore, concave down. Therefore, yes, we do have a maximum. So the second derivative test, a lot of the times, even though it's the one you're probably the worst at, a lot of times it's the fastest and the easiest one to check for these optimization questions. But yes, I did conclude that those two dimensions, they ended up maximizing the area, and I cited it, I concluded it by the second derivative test. Okay, so that was a lot of geometry. Hopefully you liked geometry. Probably not. Okay, let's move to the next one. 2 more examples. This one and then the next one, and they're both going to be pretty long. This optimization stuff isn't easy. That's why we're going to split it up and do it over. I think we did do it over just one day. But anyways, a supply of 4 meters of wire is to be used to form a square and a circle. How much wire should be used to make the square, and how much should be used to make the circle in order to enclose greatest amount of area? So again, what you want to optimize is the area. Let's draw a picture. You have some length of wire, right? It says the total length of the wire is 4 meters. Thanks IB for spelling stuff weird. But we're going to take that and we're going to break it down into 2 different shapes. I have a square and I have a circle. I'm going to call the dimensions of the square, just going to call it x. X for the side length of the square. And then I'll just say r for the radius of the circle. Now I have this, right? And you're going to kind of think about how much do I use to make the square, and then the rest of it, how much do I use to make for the circle? So the sum of this perimeter and this circumference, that total edge length, that's going to have to be equal to 4. That's not what we're optimizing. What we're optimizing is the area. But that scratchwork equation, I know the perimeter here would be 4x. I know the circumference here would be 2 pi r. So then that total edge length, 4x plus 2 pi r. This is not the thing that you take the derivative of. This is fixed. That has to be 4. So that's my scratch work equation. That's how I'm going to tie the two variables together and end up making a substitution. But what I want to optimize is the area. So let's see, the area of this square would be x times x. And then, of course, the area of the circle is pi r squared. This is what I want to take the derivative of. But there's too many variables. So I got to use the scratch work equation to somehow make a substitution. And honestly, it doesn't matter. It's about 6 one, half dozen the other. Whether I get rid of the x and I work with r's, or I could get rid of the r's and I could work with x. Either way, you're going to end up with the same result. On my notes key, I have it where I solve for x and then I work with the r's. So let's just do it that way. But if you want to get rid of the x's and then, or if you want to get rid of the r's and work with the x's, fine. You have two variables. You need to use this to substitute, get rid of one, solve for the other. But it doesn't matter which variable. It's about equally as difficult. So let's solve this for x. Subtract it over. And then divide by 4. All right, so there's your expression for x. I'm going to just simplify it a little bit. 4 divided by 4, so it's 1 minus 1/2 pi r. So I've got an equation for x. Let's go take this and plug it in. So my area, now defined only by the variable, oops, not x, it's going to be the area defined by r. Let's see, instead of x, I'm going to have 1 minus 1/2 r squared plus pi r squared. So now I've got that area equation based only on the variable r. So all the geometry and all the logic, that's done. Now we're ready for the calculus step. You can FOIL this out if you want, but you don't have to. Right now that we know chain rule, we can take the derivative of this chunk, not too bad. So let's go ahead and let's take the derivative with respect to r. And this one's going to be chain rule, right? You got something squared, so the derivative would be 2 times something. And then whatever was being squared is still inside that parentheses. And then I would need to do chain rule, the derivative of this inside piece. That derivative, that's 0, so that doesn't matter. The derivative of negative 1/2 pi would be negative 1/2 pi, or sorry, so negative 1/2 pi r, so it would be the negative 1/2 pi. So all of this is the derivative of the first piece. And then the derivative of pi r squared would be 2 pi r. The derivative area is the circumference. Spoiler alert, it's kind of cool. The derivative of, let's see, I think it's the volume, 4/3 pi r cubed. If you take the derivative, it's the surface area of a sphere. So like circles and spheres are kind of nice. Okay, so I've got this derivative. Now, remember what I need to do is set it equal to 0 and then solve. Okay, so let's put on our algebra hats and let's go through and do this fairly quickly. You have the 1/2 and the 2. Those are going to cancel. So let's see what else we have. You have a negative pi that's going to need to get distributed. So this negative, when you distribute it, and the pi that's going to get distributed, we'll have, I think, a pi squared over r, or pi squared r, right? Pi times pi would be pi squared r, and then you have the 2 on the bottom, and of course the negative times the negative is positive. Then you have the negative pi times 1. So all of this, I just rewrote, plus 2 pi r. Okay, let's take this pi and move it over. We want to get all the r's on one side, and then all the other ones on the other side. Actually, what you see, since that's pi squared, that's a pi, and that's a pi, you could just divide everything by a pi. So let's do pi r over 2 minus 1 plus 2r. That's a little bit nicer. Get out of there, pi's. Divide everything by pi. 0 divided by pi is still 0. Okay, so now let's try to solve it for r. Take that 1 and then move it over. Oops, I forgot my r there, didn't I? Then I'd factor out the r. And then all this chunk you would need to divide by. So there we got a value for r. It's kind of ugly. If you were to type it in and get the decimal, it's about 0.28. By the way, this would be equivalent if you multiply it all by 2 on the top, 2 on the bottom. This would be the same thing. That looks a little bit prettier. but those two would be the same thing. So to recap again, lots of algebra. We had the area, which we wanted to optimize, and specifically we wanted to maximize it. But it started off with too many variables. I used the scratch work to solve for x. Then I made the substitution to get rid of the x. Once I got rid of the x, then I had the area defined only by the variable r. Then I could do my calculus, take the derivative. You did need to use chain rule for this part, right? You had something squared. The derivative is 2 times something. Then you had the inside piece, which derivative was negative 1/2 pi. Then you had the other piece. Okay, so that derivative was all right. That's all the calculus right there. Then you were just doing the algebra. That part just copied. You had the negative pi, negative times negative. That's why that part is positive. Then you had pi squared r over 2. Then you had the 1 times the negative pi. Then I divided it all by pi to clean it up. Then the non-r's I moved over. Then I factored out the r so I could solve for it. Lots of stuff going on there. But I got this variable r. Once I have the variable r, come back, plug it in over here. And then I'm just going to write it down, right? If you plug in the r value, you'd end up getting the x is about 0.56. Okay, so I've got this combination of r and x. And I need to figure out whether that is a max area or a min area. So let's actually do a candidates test for this one. So I'm going to make a table. We're going to have x values and r values. And then we'll have the corresponding areas for both. Now there are some logical extremes. Right here I have the combination, the r being 0.28 and then the x being 0.56. That's one combination. Let's think about the extremes. Instead of splitting the resources, you have the 4 meters worth of wire. Instead of splitting the resources and making both shapes, it's conceivable that you may just want to forego the circle and just try to make the square as big as possible. Like, instead of splitting and having the area from both shapes, what if I just make one shape as big as possible and I just disregard the other? Right, so what if I make the r value 0? So that's no circle, but a big square. Well, okay, if the r value is 0, come back to this equation. If the r value is 0, looks like the x could be 1. So that's a logical combination that you may want to check. Then, of course, we have the critical points coming from the derivative being 0. And then the other option would be, let's forget about the square, and then let's make a big circle. So if there's no square, that means the x is 0. And let's try to figure out what the r value would then be. Again, go back to this equation. If the x is 0, you have 2 pi r equals 4, so divide it. Looks like your r is going to be 2 over pi. So I do have 3 combinations. I have the one where I make a square and a circle. Can't get the right word. So we have this. That was the special value. That was the critical point. That came from the derivative being 0. Then we have the extremes where we have no circle but a big square as possible. And then on the other hand, we have no square, but we make the circle as big as possible. So let's go find the corresponding areas and we'll figure out which one actually makes the biggest. Okay, so if you want, you could plug the x value in to, I guess you really couldn't. Just take both. Since we have both, go back and plug them in here, right? So if r is 0, x is 1, plug it in. It looks like that area is going to be 1, right? 1 squared plus 0 is 1. If you were to take these two values, which we got from the critical points, the derivative being 0, if you were to take these two numbers and plug them in, plug in the x value for x, plug in the r value for r, what you end up getting is 0.5599. And then if you end up plugging in 0 for x, you're like, okay, to heck with you square. I'm just going to make the circle as big as possible. If you plug in the r value right here, the maximum, or the area you would get for that case is 1.27. I'm going to change this so that it's 3 sig figs. So it'd be 560. Okay, so I've got these 3 answers. Obviously, I can see, hey, like that's the biggest one. So look, the combination that came from the critical point, the derivative being 0, that would actually give you the absolute minimum value. So be careful. Just because the derivative is 0 doesn't mean that that's the answer you want. This is the set of combinations that you would want if you wanted to minimize the area. Splitting the resources and making both shapes is how you would minimize the area. Actually, making the circle as big as possible, that's how you would maximize it. Okay, so let's answer the question. Remember, it says how much wire should be used to make the square and how much should be used to make the circle in order to enclose the greatest amount of area. So we could say the max area is 1.27. Are there units? Yep. Meter squared when x equals 0. That means there's no squared. And r equals this value, 2 over pi. That's how you make the biggest kind of accumulated area between the two. Okay, so that one's a little bit weird, and we checked it by really doing your candidate test. You don't have to do second derivative test. We've already done the candidate test, right? So that's fine. You only have to do one of the tests to check, and it's rare that you ever do the first derivative test. Typically, we do second derivative test, or we do the candidate test. Okay, last one. And this one's long. It's going to take up most of the page. Write small. 2 vertical posts with height 7 meters and 13 meters are secured by a rope going from the top of one post to a point on the ground between the posts and then to the top of the other post. The distance between the 2 posts is 25 meters. Where should the point at which the rope touches the ground be located so that the least amount of rope is used? Okay, so least amount of rope. That's our goal, right? We want to get the length of the rope. We want to minimize it. Let's draw a picture. So I've got some ground. I've got, let's see, we've got this post, which is 13 meters. We got this post, which is 7 meters. Now, I don't know in the middle. Like, it could be halfway, or maybe it's closer to the 7, or maybe it's closer to the 13. But there's some point, anchor point on the ground, and the rope is going to connect the 2 tops from the 2 posts. Okay, so that's a right angle, that's a right angle, that's good. I'm going to call, and we know this total distance between the 2, it told us that was 25 meters. I'm going to call this distance x. It doesn't really matter. You can either do the distance from the 7 or the distance from the 13. But label one of them as x, and then you know if the total is 25, and if this piece is x, well then your segment subtraction tells you that this has to be 25 minus x. So luckily we only have the one variable, which is x, but it's still going to be a little bit hard. Okay, but here we need to figure out what's the length of the rope, and then I need the length of this rope, and then your total rope length is your length 1 plus your length 2. Which you could find those by Pythagorean theorem. Right, ooh, Pythag, I forgot the A, didn't I? Okay, so looking at this triangle, I know this is x, and this is 7. That's your hypotenuse. So now if I did x squared plus 7 squared, and then I square rooted it, that would give me the hypotenuse. So I know that is going to be the square root of x squared plus 49. And I know the second one, let's see if I have this squared plus 13 squared. So I have 25 minus x, quantity squared plus 169. So there's your 2 lengths of the ropes, and of course we need to add them together. I'm going to call the rope r. So I take the length 1 plus the length 2. Okay, and then there we have it. We have the length for the rope. Remember, the goal is to take the derivative. The goal is to take that derivative, set it equal to 0, and then solve it. And once I have the x value, then we'll be able to answer this question. Now, this is going to be a little bit harder calculus than the other previous derivatives, but just remember your general rule. If you have a radical, right, if you have a square root of stuff, square root is the same thing as a 1/2 power. So if you were to take the derivative, it'd be 1/2 stuff to the negative 1/2. And then that you could rewrite it as 1 over 2 roots. And then whatever was inside would still be inside. And then if you need to do chain rule, your chain rule derivative would go to the top. So in general, if you have a radical, if you have a square root, the derivative is going to be 1 over 2 of the roots Whatever's inside, still inside. But then if you have to do chain rule, your chain rule derivative goes to the top. That's a pretty easy power rule. We do it so frequently, though, it's probably just in your best interest to remember. The square root gives you 1 over 2 of the roots, and then make sure you do chain rule, multiply by the derivative of the inside. Okay, so now let's go through and let's take the derivative of this r function. So I have a square root, so I know 2 of the roots is going to be on the bottom. And then chain rule, what is the derivative of the inside? That goes to the top. Okay, so the first part's done. Plus, now here we have a square root. So 2 of those roots are going to go on the bottom. And then the chain rule needs to go to the top. And this is really going to be like a double chain rule, because now you need to do the derivative of this inside piece. The derivative of the 169 is 0, so that doesn't matter. But I've got something squared. So I need to do the derivative of something squared, so that's 2 times something. And then I need the derivative of that innermost piece. So there we have it, right? That was a more complicated derivative, but it is just the power rule and chain rule. So hopefully it was okay. Remember, whatever is inside of the square root, still inside. Chain rule goes to the top. Here, whatever's inside, still inside. Chain rule, which involves some more chain rules, that goes into the top. Okay, now let's pretty this up. Let's look for things that are going to cancel. 2 and 2 are going to cancel. 2 and 2 is going to cancel. That negative is going to change this to a minus. So I've got this derivative. I've got x over the radical minus, and then I've got 25 minus x over the other radical. Then I would take that derivative and I would set it equal to 0. Now, if you have a calculator, just solve it with the calculator, right? You could say, hey, I'm just going to graph with my graphing data calculator. I'm going to find the x-intercept, right? If this was a calculator question, which it would be okay for you to go ahead and just graph this, find the x-intercept, and then you could just tell me, okay, the x value is going to be 8.75. But if you wanted to solve it by hand, which we can, here's how you would do it. Okay, a lot of algebra. Remember, if you have a calculator, just graph it, find the x-intercept. If you have a calculator, you could have just graphed the original, and you could have just found the maximum of, actually no, it wasn't the minimum. You could have just graphed this function and found the minimum, right? So GDC, you could have graphed and find the minimum point. Right? That would be fine, but then you're not showing any calculus knowledge. At least when you take the derivative and you set it equal to 0, you're demonstrating a lot of calculus understanding. Okay, so let's go ahead and let's do it algebraically, right? I need to take this chunk, add it over, and then you're going to cross multiply. Okay, so kind of just envision this. Take this whole chunk, add it over. So what you'd have is this. Then you would cross multiply. Okay, so that's what I'm going to pick up with. I've got x times okay, so there we have it. Move that chunk over, cross multiplied. Then you'd want to square both sides. Oops, 49. Am I still on the screen? Oh, yes, surprisingly. That's lucky. And then you could multiply this stuff out, and then you could try to solve it. Here we go. Let's multiply it out. X squared. If you FOIL this out using your binomial theorem, you need this times this, which I think would be 625. Then you're going to have 50 minus 50x plus x squared plus 169. Then you can multiply this out, which is the same thing. Okay, and then let's see. Those two will combine, and then you're going to distribute. So see, x squared times x squared, so that's x to the 4th, minus 50x cubed Those two combine, if you have the 625 and the 169, that's going to be 794. So plus 794x squared. If you multiply all this out, distribute the x squared, multiply all this out, distribute the x squared, let's see, you'd get 625x squared minus 50x cubed plus x to the fourth. Oh my, I'm running out of room. Then you need to multiply the 49. 49 times this number, oh, that's pretty big. 49 times 50, it's almost 2,500, minus 2450x, and then plus 49x squared, kind of fit it in. Okay, well, let's look at what happens. You have an x to the fourth on the left, you have an x to the fourth on the right, they're going to cancel. You have the negative 50x cubed and the negative 50x cubed, they're going to cancel. Then, let's see, we have some quadratic terms. So I've got that, that, and that. You'd need to get them all on one side. So you'd want to subtract this over. So 794 minus 625 minus 49. And you'd end up getting 120x squared. And then, let's see, that's the only linear term, so you'd add it over, so it'd have plus 2450x. That's the constant, so subtract it. Ooh, okay, so we got it all the way down. Now, you could try to factor. I think everything at least would reduce by a 5. I don't really want to, right? You could still try to factor and solve. Or you could use the calculator, use your graphing data calculator to get your x-intercept. Or you could use your quadratic formula. I'm running out of time and I don't really want to do any more. So there's 3 ways you really could have done this. This one, you could reduce it all by some constants and you could try to factor. It's not going to factor with super nice numbers. But either way, you're going to end up getting the x should be 8.75. You're like, Mr. Bell, if this is a calculator question, why wouldn't we just use the calculator earlier? Well, you could have, right? You could have just skipped all of it. But I'm trying to show you how you would do it if you wanted to do it without a calculator. It's going to end up being ugly, right? Since you have this quadratic that's kind of big. You could try to factor and reduce it and try to solve it. Or you could use the quadratic formula. Or you could use the calculator again. But there's a couple of different ways to get to the answer. But if you have a calculator, just use a calculator. That's fine. I would say just at least practice taking the derivative. You could have checked this original function, right? If you graph this original function, where this original function has the minimum, should be the same x value as where the derivative has the x-intercept. And specifically, that x-intercept is going to cross from negative to positive, because that's the way it would have to cross in order to have a min, right? So let's answer this question. We got the 8 equals, or x equals 8.75. So we should say the rope. I'm off the screen. Yep. The question says, where should the point at which the rope touches the ground be located? The rope should be tied to the ground. You can't just say x equals, right? Because we created that variable x. You have to define what it is, right? And here, that x, a rope should be tied to the ground 8.75 meters from the 7-meter post. So instead of just saying x equals 8.75, which the question didn't tell you what the x value was, we kind of created that. You could have used any other variable if you wanted, but we used x. You should just explain kind of what it means. Hey, the x is 8.75, so this point, it should be 8.75 from that 7-meter post. Okay, so that one was a little bit long. Again, the algebra is heavy. If you're confused, just try to graph it, right? If you graph the original, look at where it has the minimum. And then where that original has a minimum should be the same x value as where the derivative has an x-intercept, and specifically, that x-intercept should cross from beneath to above. If you wanted to solve it, you could have made some progress by hand. You would still end up with this nasty quadratic, which you could try to keep factoring. You could try to solve it. Just based on the answer, you know it's going to look kind of ugly. Or you could have just used the quadratic formula for this, which you would need a calculator, or you could have just used this, and again, could have graphed and found your x-intercept. So could have kept going, but I was kind of tired. Video's already long enough. But remember, the goal for these optimizations, no matter how tricky they are, no matter what circumstance or what situation, the word problem gives you, the goal is always the same. Take the derivative, whatever the thing that you're trying to optimize, whether you're making it as big as possible or as small as possible, you're going to take that thing's derivative and set it equal to 0, and you're going to solve it. That's going to give you your critical points, and then somehow you have to check to make sure that the critical point is the answer that you want. Or if it's not, you have to maybe do a candidates test with some other logical options to figure out what you do want. But always check at the end, either a candidates test or a second derivative test or a first derivative test, and make sure that the answer you have is correct. Because just because the derivative is 0, that doesn't guarantee you have the right answer, because that would be true for the mins and the maxes. All right, so yeah, I know those optimization ones are hard. On the homework, I believe there's 7 questions on the homework. Skip numbers 5 and 6. Right, so let's see. I'll write it down for you guys. This optimization homework is going to be brutal, so be prepared to struggle with it, and then just ask me questions, and we can work some out next time in class. So optimization homework. I think it's numbers 1 through 4, and then number 7. So skip 5 and skip 6. I have answers for 5 and 6. I think I kind of covered them up when I posted the answer key for you guys. 5 and 6, they require some inverse trig derivatives, which you guys do not have in your curriculum. So don't worry about it. If you're interested, I can send you the answers, or just go look at my. Yeah, I guess I'll have to send you the answers. But 5 and 6, they require math. I don't know why it's in the IB book, because it requires math that's not on your IB exam. But just skip 5 and 6, 1 through 4, and then 7. Those are going to be pretty tough. Try to start them and see what you can do, and then I'll go ahead and probably work a lot of those out for you. I know right away. I think number 7. I'll just let you guys go, and then we'll talk about the homework when you guys get to class.